Hello, 7th grade. Here we go. We're starting Unit 3. This is our first video. There's going to be more than two this time. We're going to take it a little bit slower. I want to go a little bit deeper. I want to make sure you guys have this, all right? Foundational understanding of forces. What moves the world? Here we go. All right. First things first, what is a force? Very simple, right? As we brainstormed in class, some of you guys had this already. A force is a push or a pull. Okay, it's acting on an object. It's between two objects, and it causes an object at rest to be in motion, or an object that's already in motion. A force can change that object's direction or speed. That's called acceleration. Remember last unit? That's why we started there. Okay? We're going to be talking about motion and velocity and acceleration. So if you're a little fuzzy on that, you might want to go back. Make sure you have that understood because forces accelerate objects. They change their motion. All right? And so we've got here a guy pushing the cart. That's a push. Got a rope around the box. He's pulling. We have two people working on the same object. One pulling, one pushing, like the dresser or box or whatever it is here. Now, when forces are balanced, there's no change in motion. Does that mean it's not moving? No. You can be moving at a constant velocity if it's balanced. If the forces are balanced on that object, then there's no change in motion. If it's at rest, it stays at rest. If it's in motion, it continues in that motion until the forces are unbalanced. Unbalanced forces are going to cause an acceleration, either a change in direction or a change in speed. Cool? All right, make sure we've got all our text. Make sure we have a well-labeled picture. Push, pull, push, and pull. Cool? All right. So, we're starting out. We're using this idea of forces. You know some forces already. This is not a comprehensive list. This isn't all the forces there are in the universe. These are some common forces that you would know, right? When we talk about a common push or pull, when I push you or pull you towards me, those are going to be applied forces. One object is exerting a force on another. It's pushing it, it's pulling it. Those are applied forces. In our picture over here, we got a little robotics car. Look at that, Lego robotics. You knew I'd work that in, huh? Here's my applied force. The motor or the engine in your car applies a force on the wheels, which applies a force on the road to make you go forward. This is your applied force. Now, there's a force that opposes motion. Friction, all right? And friction comes in four different types. You've got static, sliding, rolling, fluid friction, right? I'm not as concerned about the details of those, but that you know that there are different types of friction. The main thing I want you to know is friction works in the opposite direction of motion. So if the car is going this way, towards my applied force to the right on your screen, then friction is working opposite that to the left. All right? As things come into contact, they rub against each other, and as they rub and hit each other, they're going to oppose each other's motion. Cool? That's friction. You also know the force of gravity. Gravity is what's keeping you in your chair right now listening to this video. It's keeping your computer on the table. Gravity is an attractive force between objects of mass. Now, me and my cup of coffee both have mass, but gravity is very weak between most objects. You have to be very massive, have a lot of mass in you, all right? Have a lot of matter inside you for gravity to be very strong. That's why you're attracted to the Earth, okay? Newsflash for you, the Earth is attracted to you too. It's an attraction between the two of you, except the Earth is so massive compared to you, billions and billions of times more massive, well, that's why you're attracted to it, okay? You don't have as much of an effect on the Earth as the Earth does on you, okay? So gravity pulls you towards the center of the Earth. Gravity pulls the Earth towards the sun. They're both massive objects. It pulls the sun towards the center of the galaxy because they're both massive objects. So gravity is the force that attracts two objects of mass together. Okay, so here's my force of gravity. That's the weight of the car. When we talk weight, we're talking about the force of gravity. Last but not least, you have a normal force. Okay, this is the force that pushes back up on you perpendicular to the ground. Oops, typo. Ooh, that's an S. Pushes back up on you perpendicular to the ground. So gravity pulls me down. The force of the ground on me pushes me back up, and that's why I don't accelerate. Okay, I don't go flying towards the center of the earth because the earth pushes back up on me, the ground, and that's called the normal force because it's normally everywhere you are on the surface of the earth. Okay, if we are on Mars, it'd still be a normal force. Force of the ground of Mars pushing back up on me. Okay, so if applied forces, force of friction, force of gravity, and the normal force. If you have questions here, write them down. We'll go over them in class. I want questions. Just don't passively sit there. Get into this. Ask questions. Be curious. Cool? All right. Last slide. How are forces measured? This is a science class. I want data. We don't know anything unless we can measure it. So if we want to learn about forces, we need to know how to measure them, right? We use scales to measure them. This is an old-fashioned scale. If you ever see the statues outside a courtroom, they usually have a blindfolded woman holding up a scale, all right? And what we do with a scale is we have an object of known mass. This weighs 10 grams. And we put this on here, and if it's balanced, then the scale will be perfectly horizontal, perfectly flat going across. If it's more than 10 grams, the tail tips this way. If it's less than 10 grams, the tail tilts that way. So this is an old-fashioned scale. Okay. Nowadays we use springs or we use force sensors, but the concept is always the same. We're comparing an object of unknown mass to an object of known mass, and therefore we can figure out how much it weighs, or the force of gravity acting upon an object. We measure force in newtons. Sir Isaac Newton, they did a lot of work with motion and forces, and therefore they named the unit of force after him. All right? It just became too problematic to say 1 kilogram meter per second squared. 1 kilogram meter per second squared. Way easier to say 1 newton. But when we say 1 newton, that's equivalent to 1 kilogram times 1 meter divided by 1 second squared. So if you're a visual person, we've got 1 kilogram object here. And if I want to accelerate it at 1 meter per second, then I need a force of 1 newton. Cool? Capiche? If you don't understand it, write down a question. Ask, because we're going to be working with newtons. Cool? All right. So force is a vector quantity. It relies on acceleration. Acceleration is a vector quantity because velocity is a vector quantity. So that means we can add them, subtract them, multiply them, divide them. They are vector quantities, so they can be combined with those vector arrows, just like we did with velocity and acceleration. So we can calculate a net force. All right? Think of net like a fisherman throws his net into the sea. When he pulls it out, this is what he's left with after the fishing trip, whatever's in his net. So there might be lots of fish in the sea, but the ones that are there at the end of the day, that's the net catch or the net force. It's the resultant vector, the overall force acting on an object. So we have some examples down here. That's kind of small depending on your screen, so I blew it up for you. All right? So if I have a 10 Newton force acting to the right and a 10 Newton force acting to the left, they cancel each other out. They add up, positive 10, negative 10, for a force of 0, a net force of 0. If I have a 10 Newton force to the right and another 10 Newton force to the right, so I'm pushing it with 10 Newtons, my buddy's pushing with 10 Newtons, the resultant vector is a 20 Newton force. Notice the arrow is twice as long. Net force is 20 Newtons, both going in the same direction. Now, I could be pushing 10 Newtons to the left, my buddy can be pushing 10 Newtons to the right, and because I'm pushing more than he's pushing, the resultant vector is 2 Newtons to the left. Notice this arrow is shorter. Or that one. Should be the scale, it's not. Sorry. All right, so my net force is 2 newtons. Negative 10, positive 8 is negative 2. So 2 newtons to the left. Cool? All right, quick review. Remember, there's going to be a test at the end of the unit. These are very important questions you will see on your test. You need to know what a force is. You need to know common examples of forces. And you need to understand how forces are measured with newtons. If you don't, right now, go back. Make sure that you do. All right. If you'd like more detail, go to the book. This is chapter 12, section 1, pages 356 to 362. We'll see it in class to discuss.